Is what we did last time. We looked at the equilibrium. So hi Matt there. We looked at the equilibrium where the equilibrium constant basically tells us sorry, that was a misspelling. It tells us sort of where the reaction sits, because normally if you think about it, if you react two things together, you expect it to go to completion, and you expect all of A and B react to form C. You expect all of A and B to completely get used up to form C, and so that you only get left with C. But in real life that doesn't actually happen. It's a bit like a seesaw, where in the beginning you're going to get a lot of reaction happening because there's lots of A and B, and then as A and B slow down and there's more C, you're going to start getting the reverse reaction building up, and then every reaction has got its own sort of place in the seesaw of how many reactants there are compared to how many products. And as I say, that will also change according to temperature. So we have what we call an equilibrium constant that gives us where that position is. So take that reaction that we've got there graphed up. What we have there is AB3, because we're starting with lots of reactant up there. We're starting with 10 of AB3, okay, and that has a reaction and it forms AB2 plus B2. Now, is that equation balanced? Do I have equal atoms of A on the left-hand side to the right-hand side? And do I have equal atoms of B on the left-hand side and right-hand side? Does anybody want to have a go? Right, so it's not balanced. Correct. Because you can see I might have only got one A over here and one A over there. So the A's look balanced, but you can see that the B's are not balanced because I've got 4 on the right-hand side and only 3 on the left-hand side. So to balance that, if I put a 2 in front of there and a 2 in front of there, you should now have 2 A's on each side, and you're going to have then 6 B's on each side, because that'll be 2 times 3 is 6. And here it'll be 2 times 2 is 4, plus 2 makes it 6. So take that equation, and if I now write that equilibrium constant expression, remember what I said, the constant tells you sort of like where in the seesaw it is. What's the ratio of products to reactants? So the way we would write out the equilibrium constant for this equation, so K for constant, okay, that's the equilibrium constant, and we multiply them together. So what I really have is I've got AB2, and I've got AB2 because I've got 2 of them, and I've got B2. So those are all my products, and I have to multiply them together. Now we use square brackets to show concentration. So if you see the square brackets, all it means is concentration. So the concentration of AB2 multiplied by the concentration of AB2, because my equation says I have 2 of them, times the multiplied by the concentration of B2. And that's all over the reactants, which is AB3 times AB3. Now that gets a bit clunky. How can I simplify that? So instead of writing that all out, how can I make that a bit easier? So see Abigail's typing, so hi Abigail. You square all the AB2s and the AB3s. That's right, because AB2 times AB2 is actually AB2, come on, squared, okay? And we've only got one B2, so we leave it like that. And then we divide it by the AB3 squared, because AB3 times AB3 is AB3 squared. Okay, so whenever you write the equilibrium constant of an equation, it's always you multiply the products and you raise the concentration of the products to the stoichiometric power, or to the stoichiometric value. So I've got a 2 in front of AB2 over here, so I have to put a 2, raised to the power of 2 for AB2. Similarly, I have a 2 in front of AB3, so I have to raise it to the power of 2 over there. So for an example of a common reaction that is often given is if I react N2 and H2, come on, to form NH3. If we balance that, you'll have a 1 in front of the N2, a 3 in front of the H2, and a 2 in front of the NH3. So if I had to write the equilibrium constant expression, then what would that be? So you always look at the products first, and then they all in the numerator at the top, and then the reactants are on the denominator. So what would go on top? Anybody want to have a guess for that reaction? NH3. Well done, Nicholas. So it's NH3, because that is the product, and the square brackets means the concentration of. Now, do I have to raise that? I have to square it, correct. Because I have that 2 in front of the NH3, I have to raise my concentration by squaring it. So I'll raise it to the power of 2. Okay, then I divide it by my products, and so what would go as the denominator? Right, so it'll be N2 and H2 cubed. So because you have to do calculations with this, I hope you know how to use your calculator for cubing and squaring. Now, it hasn't come up often. Well, I haven't actually really seen it come up much. It's more that you have to write the equilibrium constants expressions, but you may have to do calculations, particularly of the more simple type of equilibrium constants. So you wouldn't get, raised to the 4th power or anything like that. Okay, now a bit of terminology, of way of writing. When you write an equation, then make sure that, I'm just going to highlight it with this yellow, make sure that you use the equilibrium arrows. So if you're talking about an equilibrium where the reaction is in a sort of like seesaw between the products and reactants, okay, because when something is in equilibrium, what happens is we don't see a change in the macroscopic level because it looks as though it's gone to completion, but it just means for every forward, where the reactants react to form a product, another product is breaking up to form the reactants again. Okay, so we show that by showing a double, an arrow going in 2 directions. I know in some, especially on the internet, they tend to use this sort of arrow a lot, but please don't. I know it's used because of like the internet and so on, but it's not the standard form. Always use the standard form of the double arrows, you know, 2 arrows going in each direction. If you wanted to, you could write it like this, but again, that's not ideal. We're sort of showing like a half arrow in each direction to show that it's not, hasn't gone completely to the right-hand side, and it hasn't gone completely to the left-hand side. We're sort of trying to show it's somewhere along that continuum. It may not be in the middle, it may be much more towards the right-hand side or much more to the left-hand side, but it's somewhere along there. So that's the first thing in terms of how to write things with equilibria, is use the proper arrows. The second thing is make sure you use the square brackets to show concentration. Okay, so don't write things like K is equal to, and then you just use the ordinary brackets, NH3 squared, because we use the square brackets to show concentration of. Once you've substituted a number in there, you can use the round brackets, because you've now put in the concentration. So let's now do some calculations with the equilibrium constant. Are you all clear on how to write an equilibrium constant expression? Writing the products raised to their power over the reactants. Okay, so we'll just tidy this up a bit by getting rid of it. Because I'll just work this out over here. Right, so if you look at this graph, and I'll just move it up a little bit, you'll see that in the beginning it wasn't an equilibrium. I had lots of my AB3 and I didn't have any reactants. Oh, sorry, any products. So right from the beginning, but because I had lots of reactants, a lot of AB3, there was a fast reaction happening, and so a lot of it was converting, so we're getting less and less of the AB3. But then as we're getting fewer and fewer particles of AB3 remaining, you can see it's sort of slowing down. And then I reach this plateau over here. And the same thing with B2. Notice how we had nothing in for B2, but then it increases, and then it also reaches this plateau. And then the same thing with the AB2. It also increases at double the rate, and we have double the amount of AB2. Let's first ask, why do I have double the amount of AB2 compared to B2? So B2 is sitting at round about 3, and AB2 is round about 6. Why do I have double the amount? Why didn't I get equal amounts? Right, Abigail, correct. You always look at the equation and you'll notice that I've got 2 AB2s formed for every 1 B2. So I must get double the amount of AB2. Okay, so that's the first thing. The second thing is it's reached this plateau. What does this plateau mean when it's gone flat? What is happening in this area? Now it doesn't matter if you're not sure, because I did do this last time, but it was 2 weeks ago, and I went over it quite quickly because I was really focusing on Le Chatelier last time when we changed conditions. So now I'm just working on the actual constant itself. So, okay, Thomas, right, it's an equilibrium, and Abigail, you're also correct, there's no longer any overall change. In other words, on the macroscopic level, you don't see any change. It looks as though the reactions come to an end. But what's happened is that now for the rate of the forward reaction is equal to the rate of the back reaction. Okay, so it's because the rate is now equal, we don't have this change of amount over time, because that's what rate is. Okay, how fast the reaction is going. So with time, what are my changes? It's now at equilibrium. Now if I have got the equilibrium concentrations, I know it says amount, but let's all assume it's all in 1 liter, so we have a concentration. If we have it now in equilibrium, can I now calculate the value of K for this reaction? Yep, because I've worked out the formula of K, okay, over here, and I have now got values that I can substitute, and because it's at equilibrium, it now, will, I just have to put it straight in. So if we were calculating this, always, as I say, I have the what I call the eq method. Okay, if you see a calculation like this, you can welcome to say eq. And the eq is, first of all, make sure that if they haven't given you the equation, which is unlikely, I'm sure they would have given you the equation, they give you write the balanced equation first, okay? Because you need the balanced equation in order to do the next step, which is write the expression. So this is what we call the equilibrium constant expression. So it's in alphabetical order because an equation starts with EQ and an expression starts with EX. So EQ comes before EX. So equation first, and then you can write the expression so that you know what you can raise the power to and so on. So I'm going to just repeat my expression here just to get that, solidified. Make sure that you have the correct expression. And even if, say, in the first part they asked you to write the expression, and then like in part A, and then in part B or part C they ask you to do the calculation, write the expression again, because I was actually marking somebody's this morning and they had done the correct expression in one part of the question, but when they had to do the calculation they forgot to do the squaring, or they forgot to put in another both products, so only put in both reactants, so only put in one reactant. So always write the expression and then substitute. So now if we look at this, at our equilibrium here, we know AB2 is equal to 6. Okay, we know B2 is equal to 3. So now I can use round brackets because I've now put in the concentration. So I multiply that by 3, and it's all over the AB3, which is 4. And I have to raise that to the power of 2. So, as I say, if you write the expression first, you hopefully won't forget to, do the squaring. So now just do it in your calculator. This one you may or may not be able to do in your head, but pretty much 6 times 6 is 36. Okay, times 3. Whoops, I did the wrong thing here. So you should have something like 108 divided by and sorry, I should have been able to do that in my head. 4 times 4 is 16. And you should then get an answer of 6.75. I don't know if any of you have been able to do that one. Have any of you done the calculation with me or not? Because it's good to do that squaring so you know that you know how to use your calculator correctly. Because every calculator is different, and that's why I don't give instructions on how to use your calculator for it, because it can vary. Now, a few things to notice with this. Notice I have not put any units down. Okay? You have units for concentration. What are those units, by the way? If you've done the CH2012, you should know it, as well as the CH2001, 2062 I think has it in. What would be the units for concentration? I know some of moles per liter. Correct, Thomas. So concentration has a unit, but the equilibrium constant doesn't have a unit. When you get to university, then yes, you do have units, and it, you know, you have these cubes and squares and things all over the place. But as far as NCEA school going goes, we ignore the units. So you don't give a unit when asked to do an equilibrium constant. So that's the first thing to notice. The next thing to notice is the size of the equilibrium constant, because they could ask you questions about it. Is that equilibrium constant value bigger than 1 or smaller than 1? It's bigger than 1. So, do you think we've got more products or more reactants? It favors products. And you can see that. I mean, I know you seem to have more AB3 than B2, but overall, if you had those sort of, average those, you would have more of the products than you would have of the reactants. So you would say your equilibrium position lies to the right, towards the products. Okay, so that's sort of two things once you've done your calculation, is to work that one out. Now, let's work it out again using this and this and this area. Okay? Just based on what we did last time, what do we notice happening? We notice that there's an increase in the reactants and there's a decrease in the products. Is it a sharp, sudden increase or decrease of any of them? In other words, is it because I've suddenly added more reactant or I've added more product? No, it's a gradual one. Okay, so if it's a gradual one, it is probably something like a temperature change, and we can work out that in a number of ways. So the first point about a temperature change is this equilibrium constant is only a constant at a particular temperature. For example, if I said, what is the pH of pure water, what would you actually answer? 7. And that's the standard thing. But actually, that's only the case at 25 degrees. If I have hot water, boiling water, or if I have water near freezing, the pH is not exactly 7. It would be slightly higher or slightly lower. And I must admit, I've forgotten which way it goes, which one's the more acidic one. I think the colder water is more acidic and the hotter water is more basic. By that, I don't mean the water is actually acidic. Just to explain, water is always in equilibrium with hydronium ions and hydroxide ions. So my negative charge is not staying there. Right. So it's always in equilibrium over there. Now, at 25 degrees centigrade, my concentration of this is actually 1 times 10 to the minus 7. And my concentration of the hydroxide is the same. And can you see, therefore, where we get the pH is equal to 7 from? Okay, it's from that 10 to the minus 7. Next week, or perhaps later today, but definitely next week, we'll be doing pH calculations, and then you'll see how we get that. Okay, but say my equilibrium shifts towards the left, so I've got more water. So I've got more water and I've got less of that. So say it's now 1 times 10 to the minus 8. Okay? And my OH minus will also be 1 times 10 to the minus 8. So it's still neutral. Okay? But what do you think my pH is going to be now? Our pH will be 8. So actually you can have neutral water with a pH of 8, and you can also go the other way and have a neutral water. It's actually not that high. I mean, I've exaggerated it. It's only, it goes to 6 point something, and because water only varies between 0 degrees and 100 degrees, and then you can't sort of measure it sort of in between. But what I'm trying to say is the equilibrium constant of where that sort of thing lies depends on temperature. And if I change the temperature, I'm going to change where, my ratio of products to reactants. So that was just as an example, and it's sort of like trivial fact. You can ask now your mates and say, is the pH of neutral water always 7? And if they say yes, you can say, but sometimes it's not. It's only at a pH of, at a temperature of 25 degrees. Okay, so let's now work out by doing the same calculation again. So we've got K is equal to AB squared, or AB2 squared, oops, I'm doing the wrong arrows there, not wrong arrows, wrong brackets, all over AB3 squared, and now I put in my new values. So what is the value of AB2 now? If you read this graph, this is, I don't know if it's clear enough for you to see. That'll be 1, 2, 3, 4, 5. So it's 1.2, 1.4, 1.6. That may have been a bit difficult for you to see. So it's 1.6 squared, and whoops, yep, so there was 1.6, and your B should be now 1, 0.2, 0.4, 0.6, 0.8, 0.8. Do you agree with me, or do you find it a bit too difficult to read? Does that make sense when you count up? Okay. Can you see that clearly, or is it actually just too difficult? It's too small. Yeah. Okay. Right. And then I divide that by my AB3, which up here is now, if that was 8, it's 8.2, 8.4. So it's 8.4. Come on. There. Squared. So, does anybody want to do that calculation? Okay, great. So I get 2.048, just in case people were going in there, and then it's 8.4. I've still got an old-fashioned calculator here. And that's 70.56. And I'll just move all that out. And yes, you should then get that answer. That sounds correct. 0.029. Okay, so I'll just double check that, but it should be. Yep. Okay, so well done. If you were asked to do 3 significant figures, if everything had been given to 3 significant figures, then it would have been 290. Just be aware of significant figures. This actually has not been given to 3 significant figures, so 0.029 would have been fine. Now, has this value changed to the one above? Yep. And if we have a change in K, the value of K, it means we have changed the temperature. Okay? Because if we had changed it by changing the pressure or changing the concentration or changing the volume, doing any of those, you wouldn't actually change the value of K. These figures may change when you do the amount of AB to B2 or something like that, depending on what you've done, but your K value should actually then remain constant. Okay, so that's the first thing. So we know that because our K value has changed, our final calculation, it means that we've got a change in temperature. So the next question is, have the reactants been favored or have the products been favored? So the reactants have been favored, correct, because we can actually sort of see we've got a lot more of the AB3 being formed. Okay, so we know that the equilibrium position has shifted towards the left to form more reactants. So just based on what we did 2 weeks ago with Le Chatelier, is this reaction exothermic or endothermic? So exothermic means heat is released. Endothermic is heat is taken up. So when I say is this reaction as written. So if I'm doing the reverse reaction, that's what's happening. It's going more towards the reactants. That's the favored one. So if it's going to go that way, has my temperature increased? Well, hang on. I would actually, you'd have to know one of them. So I'd have to actually tell you that there was either an increase in temperature or a decrease in temperature. So we could work this out 2 ways. You'd have to know one of those facts. You'd have to know either whether it's exothermic or endothermic, or you would have to know if the temperature has been increased. Sorry, I suddenly realized you weren't given one of those things. So let me say the temperature increased. So what I did after 16 minutes is I heated the mixture. So knowing that fact that I heated the mixture, and so the reverse reaction was favored, what can you tell me about the reverse reaction? Is it endothermic or exothermic? It's endothermic. So remember with Le Chatelier is if I put a change into the system, the reaction is going to, or the equilibrium position is going to move in such a way as to minimize that change. So if I'm adding heat, the reaction is going to try and absorb that heat. And that's the endothermic reaction. So if it goes towards the left, towards the reactants, it means that must have been the endothermic reaction to try and absorb my added heat. Okay, so this is a sort of summary also of what we learned last time with Le Chatelier, of being able to work out what's happened at all these different points and looking at the K values. So do you think you can work out an equilibrium constant expression, and then B, can you substitute values into that and then work out what has happened? Okay, well, I'll just do one more sort of thing that you need to go, and then we'll do another problem. Sometimes you could be given where you won't be given a graph, but the question may ask or tell you that the equilibrium constant is, let's say, I shall just erase this just to make it a bit tidier. So we say there's a particular reaction and your equilibrium constant is 130. Okay? So you are told that the equilibrium constant is 130. Now you'll find, by the way, which I forgot to mention, sometimes the equilibrium constant is written as Kc. That C just simply stands for concentration. So if you see Kc, it just means the equilibrium constant in terms of concentration. So say you are told the equilibrium constant is 130. And then you are told you are going to mix together so let's do the same reaction of AB3 going to, come on, why is it not going there? AB3 going to AB2 and B2. So let's say we'd mix together some of this, and some of this. And you want to know, and you get asked, which way will the reaction go? Will the forward reaction be favored or the reverse reaction be favored? So the system isn't at equilibrium yet. You are just going to throw three things together. So say, and I'll just tidy this up and I'll just write the values underneath and then we'll do the calculation. So say my values were 1.5 of this, and I had 3 of that, and I had 0.5 of this. Okay? You need to work out then what the K value is. Sorry, that should have been point. What we don't really call it a K value if it's not at equilibrium. We can either call it a Q or an IP. So that's just the product. Let's just call it Q for a quotient. That's a common one. So this is just for values that are not at equilibrium. So I can still work it out. I can, by calling it Q, it is still 3 squared times 0.5 all over 1.5 squared. And if you'd like to do that calculation, what is your answer? Did you get an answer of 2? I haven't. Okay. Did anybody else get an answer of 2? Because I was just making that up in my mind, in my head. Yep, okay, great. Okay, so there's a nice simple figure. Now, as I say, this is not at equilibrium, and this reaction is still happening, and it's sort of somewhere in here, this area where it's not in equilibrium. So you've got to work out, am I going to have the forward reaction, or am I going to have more of the back reaction happening when I throw all this together? So you look at Q and you compare it with the given Kc value. Is the Q value bigger or smaller than the Kc? So is 2 bigger or smaller than 130? It's smaller. And because it's smaller, it means that the forward reaction is still favored, because I've got to get more and more products being formed to try and up this figure to 130. Can you see that? So more and more of this has to react to give me more and more up here. I must make this number bigger and this number smaller to try and get this number up to 130. Does that make sense? I've got to increase the numerator values and decrease the denominator values to try and change 2 to 130. Does that make sense? Yep, okay, because I want to have a bigger number, so the one on top must get bigger and the one at the bottom must get smaller. And the only way it's going to do that is if the reaction goes forwards towards the right, towards the products. So I get less reactants and more products. If I had worked it the other way, so say my answer, you know, the values I had here, say my answer was when I threw all these three chemicals together, and say my value came up to be 200 instead of to 2, what would happen then? Would I still get a forward reaction, or would it start going more towards the reverse? It'll get more towards the reverse because 200 is bigger than 130. So I want to make then this whole thing smaller, which means I have to make the denominator bigger and the numerator smaller to try and get 200 down to 130. So the only way I can do that is by having less of this and more of that. So I'm going to have the reverse reaction happening. So does that sort of make sense, that you can compare when something is not in equilibrium and you just get given values, you can work out which way it's going to go. Okay, right, so this has been quite in depth. I don't think you're going to get really many things this difficult. I'm going to just quickly show you some past papers, just so that you know it's actually not that bad. And let me just bring up so I'll make this a lot bigger. So this is for this 9116 standard, and you'll notice generally the first or second question is always on rates, which is on the 2061 booklet, and you'll see this is on rates because you're changing the temperature and so on and so forth. And then, so that's all on rates, and it's normally a whole question on rates, and then they'll start doing either on acids and bases and then or on an equilibrium one. Here they've done acids and bases, which we haven't dealt with first, and which we haven't dealt with. Right, I wanted to come over here. Sorry. Okay, here is what happened last year for an equilibrium reaction. So they've I suddenly realized I actually can't write on this. Okay. But we can still talk about it. If you get given the Kc, remember the C just stands for the equilibrium constant using concentration, you have to write the chemical equation. So what would that be? So remember you had to, what's on top, the numerator, are the products, and what's at the bottom are the reactants. And these little numbers up here, the 2 and the 3, are the stoichiometric values. So does anybody want to type in the equation? So a few of you are typing. Right, A, yep, plus 2B, correct, because that 2 is from there, and those are the reactants, great, goes to 3C plus D, brilliant. Okay, so, you know, remember to work it both ways, because I think a lot of people always are used to, given the reaction and, you know, make the Kc value or the Kc expression, but you can be asked the other way around. And now here is something similar to what we did last week. We told it's in a closed system. Why is that important? For an equilibrium to exist, what are some of the requirements? Not too sure? Okay. One of the things is, of course, it must be in a closed system. So, you know, the closed system could be the whole universe if we were doing, you know, things on a global scale. But otherwise, it's like doing a reaction, a gas reaction in an open beaker. It's never going to reach equilibrium because the gases are going to keep on escaping. So you'll never get the forward and backward reactions rates being the same, because they can escape all the time. So closed system is important. Sometimes a closed system can be fine, you know, just located in a solution, as long as that solution can't evaporate and therefore change the concentration that way. Okay, so we get given the equilibrium, and notice there's that equilibrium arrows again, so try and make sure you have those correct. Then explain using equilibrium principle the effect of adding more ethanol. So this is this Le Chatelier. And for ethanol, you're told that's the ethanol. Okay, if you don't recognize it from organic, you are told it over there, so otherwise it's over there. So if I add more ethanol, I'm adding more of a reactant. So what would you say in answer to this? There's a few things you have to mention. You have to explain what Le Chatelier's principle is. So mention Le Chatelier and what it is. So Le Chatelier's principle explains what happens to a system in equilibrium when a stress is added, because the equilibrium position will shift in such a way as to minimize that stress. So here the stress is adding ethanol, so we have to, or the reaction will try to remove the ethanol, which means that the forward reaction is favored, and we're going to get more products. So the equilibrium position will shift to the right. Do you think you'd all be able to answer that type of question? Yep, okay. Right. Now they're adding a catalyst, and again, so it's using equilibrium principles. So catalysts, you know, come up with rate. Okay. But if I add a catalyst, is it going to change my equilibrium position? Not too sure on that. No, correct, Thomas. It won't. Adding a catalyst, removing a catalyst doesn't affect the equilibrium position at all. What it does do, though, of course, is it increases the rate of the reaction. So you won't see any effect overall. Okay, it'll all look exactly the same. But what's happening if you add the sulfuric acid as a catalyst, then the reaction is going to go to completion a lot faster. So if it wasn't in equilibrium, it will now get into equilibrium much faster, because we're increasing both the forward reaction and the back reaction, and once it's in equilibrium, the forward and back reaction is happening a lot faster as well. Okay? So if, going back here, if I added these two together without the sulfuric acid, it won't be in equilibrium straight away. It might take hours or days to get into equilibrium. Whereas if I added the concentrated sulfuric acid, it would happen a lot faster. But once it's in equilibrium, there's going to be no visible change. It's just the forward and back reactions are happening faster, at a faster rate, but still an equal rate. Does that make sense? Okay, not too sure. Okay, so now here's an example where you get given calculations. So there they give you the values. They ask you for the Kc. Okay, and then so this is exactly like what I did in my last example. So the SO2 you get given a value, the O2 you get given a value, and the SO3 you get given a value. And you're told what Kc is. So if you were working this one out, as I say, I really thought I could write onto it, so I didn't download it. I might actually download it very quickly. So we've got 5 minutes to, so I'll just do it to the desktop. Sorry, my desktop is so cluttered. I should have actually perhaps not done it to the desktop. Not that one. Okay, I don't want to waste time. Sorry about that. I don't know where it's disappeared to on my desktop. Okay, so let's just work this out, because we've only got sort of 5 minutes or so remaining. If we did the Kc expression, would you get SO3 squared over SO2 squared plus O2? Times O2. In fact, I'm quite glad I said that plus O2, because remember it's multiplied together, not added together. So do you agree it'll be SO3 squared? So if I did that and you did the calculation, what do you come up with? So it's 0.25 times 0.25, because you've got to square it. So I get a figure of, for what should be on my numerator, 0.0625. And then so don't forget that one. And then you'd do the same thing, you'd square your SO2. And did you get 0.09 for that? And you multiply it by the oxygen. Okay, of that, so it's So your denominator is 9 times 10 to the minus 3. And if you worked it out, then your final answer would be did you get 6.94? I'm doing it pretty fast, so I may have made an error. You got it, great, 6.94. Okay, Kc though, you are told, is 4.32. So, is it in equilibrium? No. I mean, you're correct, it's not. Okay, you're told it's not in equilibrium, and you have to justify why. So, the reason is your Kc values are not the same. Okay, so this, as I say, is you're told it's at 600 degrees, so you know you haven't changed the temperatures. So you know these concentrations, it has not reached equilibrium yet. Okay, and so what would happen in order to get it to go to equilibrium? Would the forward reaction be favored or the back reaction be favored? So think of 6.94 compared to 4.3. Which one is the bigger value? Okay, and Abigail, you already answered the question. The back reaction would be favored because my Q value is bigger than 4.3. So the only way to get my Q value down to 4.3 is to have fewer products and more reactants. So I must increase what's in my denominator and increase what's in my numerator. So those are the sort of calculations you can get, and there is how will it, so we now do the effective temperature. So it's at 450 degrees. So how does the change in temperature affect the value of Kc and the position of the equilibrium? So again, you've got to look to see, is this an exothermic or an endothermic reaction? It's an exothermic reaction, correct. So if it's an exothermic reaction, now I hope I'm going to get this right because I know I sometimes muddle myself up. Would the K value get bigger at a higher temperature or smaller at a higher temperature? And actually, as I say, I tend to always muddle myself up on this one. So I will just be very sneaky and go, if you look at the assessment schedule, very sneaky. I hope all of you know about where to find assessment schedules and so on. And I'll just make it bigger. So, right, at 450 the temperature has decreased. So it was at 600, it's now at 450. And okay, Thomas, you answered that question. I know I can get myself confused. So we know the reaction is exothermic because we were told it was a negative value. Okay, so if the temperature is decreased, then the reaction will move in such a way as to produce more heat. Okay, and because it's an exothermic reaction, then the exothermic is forwards, and so you're going to get more products. And if you've got more products, the value of K is going to get bigger. Okay, so we've gone through the calculations pretty quickly there, and yeah, you see here what they've done there with it.